Jadavpur University, and I request Professor Rabindra Nath to chair the session.
Good afternoon. This is the last and fourth plenary lecture will be given by Dr. Rabindra Nath Gayen. He is an associate professor at the University of Jadavpur University, and he was also our colleague, and unfortunately left us. So that he will talk about some ternary compounds. CZTS, 4 elements are associated there, and this is the 4th lecture. So there is a coincidence, and this is a good and established photovoltaic materials used in photodetectors and solar cell applications. I hope we will enjoy by his lectures. So I will request Dr. Gayen to speak about that CATS things. Dr. Gayen, please.
Okay, so thank you so much, Rabindra. It's really I feel honored to be here. The students invited me, so I'm here. This talk is meant for the students only. So maybe going for experts, but that's I think statistically approved. Most of the questions are from students community. So today I will talk about some basic phenomena that all of us are aware of. That is the photovoltaic effects. From our school days, we know about this. Now, how these photovoltaic effects are used in devices like solar cells and other photodetectors kind of things and materials. You know that any kind of technologies basically depends on the properties of the materials. Any kind of technology that use some specific properties of the materials for certain purposes, right? So the materials are important. Yeah. So I'll talk about the materials and photovoltaic devices made of some materials, and specifically I'll mention about one material that is emerging material, CZTS, that stands for copper, zinc, tin, and sulfide. It's a quaternary semiconductor material, and their uses as photovoltaic devices, right? So we have a piece of material, and oh, sorry. I think so we have a piece of material and just trying to fly, and you're getting the electrical energy or current or voltage or whatever say. So how this is a fascinating phenomenon of photovoltaic that you all know. So in this talk, I'll initially introduce the photovoltaic effect and the material that shows the photovoltaic effect and some devices, some emerging photovoltaic technologies. That means some device structure that efficiently convert the light energy into the electrical energy, electrical power. And thin solar cell, and obviously I talk about the CZTS, a special material that shows efficient photovoltaic properties, that means efficient conversion of the incident and light into electrical energy. So how to convert light into electricity? These two are the basic phenomena that you all know. Photovoltaic effect that is called by Becquerel in 1839, long ago. So it's basically the electron transition. That means the creation of electron-hole pair upon incident light. So if electron inside the semiconductors are the materials here. Semiconductor incident photon, it absorbs electron absorbs the incident photon, and if the incident energy of the incident photon is greater than that of the band gap of the semiconducting material, the electronic transition occurs. So it's a quantum mechanical process. And another way we can get charges, that means from the light, is photoelectric effect. All of you know about the Nobel Prize of Einstein, the explanation of the photoelectric effect, that the electrons are ejected from the surface of the metals if the energy of the incident photon, incident light, is greater than the work function of the metal itself. So in photovoltaic effect, the charge carriers that generated are inside the material. That's not going outside the material, right? For the photoelectric effect, we are getting the electrons ejected from the material, right? So if you want to get an electric current out of that, so you have to make another arrangement like photomultiplier. You know about it, and but for the photovoltaic effect, you can get the electron hole pair. That is the basic. That is the concept, the creation of holes. And that is the bottom line of the photovoltaic effect. Now, semiconductor is the key player here. You know that the concept of hole stands for the semiconductor only. And when we talk about the semiconducting materials, the band structure takes the most important role, and it's a quantum mechanical model, as you understand that. So the optical, the electronic transitions, that means electron goes from the valence band to the conduction band by absorbing the photons, right? So the primary condition is the band gap of the material must be such that the incident energy should be greater than the band gap of the material. That is the primary condition. Now, when electrons are going from the valence band to conduction bands, basically, so there must be some unoccupied space in the upper stage, and it must follow the quantum mechanical selection rules available. So the basic principle, the bottom lines of the generation of the electricity from the light is these two lines. The generation of electron hole pairs, that's the generation of charge periods, and we have to get current or voltage out of these charge periods, right? So charge periods, you have to move the charge periods. Who will do this work? The separation of charge periods, that is it. Now the generation of charge period is basically due to the electronic transition that is said. That is the point. Now, a simple junction, that is a P-type semiconductor and N-type semiconductor junction, at the physical junction, there is a depletion region, that is, you all know that the formation of the depletion region, and at the depletion region, there is an inbuilt electric fields there. Now, this field, if the electron hole pairs are generated near or at the depletion region part, there is inbuilt electric field, and this electric field applies force to the charges in opposite directions, and the charges get separated. So by some means, if we can get the separated charges, that means the photo-generated electron hole pairs that cross this physical thickness of the layer, and if they can be transported to the outside circuit, we can get the current out of that photo-generated charges. Okay, and the voltage, obviously in the depletion region, we have the barrier potential height that gives you the the voltage part. So this is a simple form of device that can detect light as well as that can give you the voltage also out of this. This is the basic electric field at the heterojunction, at the junction. And so these two are the basic principle of any optoelectronic devices. So due to the light, electron hole pair creation and the separation of the electron hole pairs to the outer circuit to get the current. Okay. So the materials are the, as I mentioned, the materials are the most important part of the in any kind of devices or technologies. So the band gap. So when you choose a material for your optoelectronic application, you have to first consider the optical band gap. So the band gap has to be such that the transition, the electronic transition occurs, and you get the charge carriers inside the material. And high absorption coefficient, the material must have the capacity to absorb more light with less physical dimension. So this is basically the amount of light being absorbed in the material that is defined by the absorption coefficient. High carrier mobility, the electrons or the charge carrier, when electron hole pair generates, it tends to recombine very fast. There must, I mean, the mobility of the charge carriers inside the material must be higher so that we can get the current. Carrier lifetime has to be longer. So the carrier must exist. The photogenerated charge carrier must exist longer time inside the material so that we can get the possibility of getting current out of the photogenerated charge carrier are high. Recombination rate should be lower, and there is some technical part. I mean, the some if we are fabricating any device the fabrication process has to be cost effective, and you know about the any technology in recent times or any technological development should be environment friendly. So the materials should be environment friendly, should not contain any toxic elements and eco-friendly. Okay, and stability of the material is very important because these photovoltaic materials, we are talking about the conversion of sunlight into electricity. So if it wants to compete with the existing source of the electrical power, that is the fossil fuels and all those things, so the cost must be reduced or unit cost. Okay. And there is another aspect that you all know about this, that people are using nanostructured materials for various device applications. So nanostructures are how nanostructure is different from their bulk counterpart. Basically, the physics people will talk about this quantum confinement in the nanostructure. So if you reduce the dimension of the material, after critical dimension, the properties of the material changes. So it becomes a new material compared to its bulk counterpart. So what is quantum confinement? Now think about this two-dimensional structure. So one dimension, I mean the thickness has been reduced to such that the density of states is a continuous function, a parametric function that you know for bulk material is become like a state function. So the density of states are different. So that means the properties of this material is different from its bulk counterpart. Actually, who defines the properties of any material? It's the electronic behavior in true sense. How electrons behave inside the crystal structure or material that defines all kind of properties of the material. Right? So when an electron is free, it has, and when an electron is actually inside the material, it behaves differently. So, and that defines all kind of materials. And you are most of you are theoretician. So basically, that is the theory we're trying to develop. Actually, the electronic band structure. So the density of states are different, and if you reduce two dimension, and what you see here that the anisotropy induces because of the reduction of the dimension. For the two-dimensional case, it's like a thin film, it's a quantum well, so electrons are confined in this direction, right? And in the XY direction, its electrons can move freely. So the direction dependence, the properties comes to arise. This is called anisotropy. For one-dimensional case, this is the nanowires. This is quantum wires. You say the density of state function is again changing, and you know about the quantum dots, that is zero dimension. All the three dimensions are extremely small, so it's absolutely quantized, and so it behaves like a discrete energy states are there. Now, so I talked about the photodetectors and solar cells. So basically, the photodetector, I mean, solar cells is one kind of photodetectors. It can detect the incident radiation, the device that can detect the incident electromagnetic radiation. That means due to the illuminated by the incident radiation, if the properties changes, so that is a photodetector. So incident electromagnetic radiation, it can detect. That is the photodetector. Solar cell basically acts as a power supply. So solar cell, from the solar cell, you can get not only current but also the voltage. So basic working principle is photovoltaic effect. In case of photovoltaic effect, that can be a photodiodes or solar cells. Okay, and photoconductive effect. So that can only detect the incident radiation, there is no need to get the voltage out of that. So only the change of resistance or conductivity due to the creation of the charge carriers inside the material. So that is the photoconductivity. Now, semiconductors are the key player for this kind of devices that you mentioned. And we know about the elemental semiconductor, there is only two, silicon and germanium, and the compound semiconductors which have been used for this kind of optoelectronic applications are 2,6 compound semiconductors like zinc oxide, titanium dioxide. They have a wide band gap. The band gaps are higher, of the order of 3.2 electron volt at the room temperature. So we need more energy for the electronic transition. Okay, so they can detect basically the UV range of light. And 3,5 compound semiconductors like gallium arsenide are very popular for the optoelectronic application because of their very high mobility, electronic mobility. So the device becomes faster. And some emerging materials like perovskites, crystalloid structure that we are talking about, that is CZTS, 2D materials like graphene, MOS2, they are being used. They are being used recently for as emerging material for device applications.
How much time the crystalloids
Okay.
crystalloids when did it emerge as a possibilities?
Crystals are being studied for few years right now. It is now a established material, well established. Right now, people are trying to improve the efficiency out of the crystalloid material using some optimization. Okay, so that I will talk about in later. I will mainly focus on the crystalloid structure, that is the CZTS that we say. So these are the conventional characteristics of a photodetector. If you are developing a photodetector, you must have to check its responsivity, how efficient your device is, and how efficiently you can convert the input light power into output electrical power. That is the primary thing. And quantum efficiency is basically the number of charge carriers that is being generated by the incident photons. So we have 100 number of photons being incident, and how much out of that photons are actually being converted to the charge carriers. Not all the photons are able to electronic transition. Okay, able to have the electronic transition. Dark current should be low, noise should be low, response time should be very fast. So that your device should respond very fast to the incident electromagnetic radiation. And spectral response is another important parameter that gives you the sensitivity of the photodetector as a function of the wavelength of the incident light. So wide range of electromagnetic spectrum if it can detect, so that is good for broadband photodetectors. So it can detect broad range of electromagnetic spectrum. So you know that photodetectors have various applications: communications, camera detectors, and UV sensor, as environmental monitoring. And now recently, people are trying to develop about the self-power photodetectors. That means we don't need any external bias voltage or power for the detection of the incident light. Okay. So it's self-power. That means you just illuminate it with light and you get the current control. And obviously the sensitivity has to be higher, the response has to be fast, and it can detect wide spectral response. That is the target. So that is the challenge. So it must be cost-effective, efficient, and stability is another issue for the development of the materials. Okay. Now we basically focus on the photovoltaic devices or solar cells because that is the broader application aspect of the photovoltaic technology. So if we think about the solar cell, so we must have to know what is the composition of the solar energy. That means the light we get on the Earth's surface from the sun, mostly it has a visible range of light. Right? So when it travels through the atmosphere, UV part and the IR part gets absorbed. Right? So what we get on the Earth's surface is mostly the visible light. Mostly the visible light. This is the energy spectrum, the solar energy spectrum. Now, if we can able to convert a very tiny fraction of the solar energy we are having on the Earth's surface, that is actually sufficient to meet the requirement of the global energy needs. So that is the possibility of solar energies. Okay, and the sun showers more energy on Earth in 1 hour than the global energy need in a year. And the solar energy is the most reliable resources of renewable energies on the Earth that we can say, and the most promising candidate to replace the conventional energy sources, that is the fossil fuels or coals, whatever you say. They are depleting very fast, as well as as well as the environmental concerns are there, right? So they can be the right candidate for getting the green energy technology, I mean green energy sources. So we have to, the challenge is to get the solar light and convert the electrical energy with better efficiency at a modest cost. Now here comes the challenge basically to get the efficiency of the cells. This is the global energy map. So if you just look at the position of India, we are very lucky to have the abundant solar energy throughout the year, and some of you must have aware of the National Solar Mission declared by the Government of India in 2010, and there's a target to install, to get switch to the renewable energy sources, and a major component for that is the solar energy. And right now, India is among top 5 countries who are installing, who are investing on the solar cells and solar energy devices. So if we take a closer look at the solar radiation spectrum, as I mentioned, it mostly consists of the visible part that we get on the Earth. So we have to choose the material with suitable bandgap. They can convert the visible light into electrical power or energy. So a single PN junction can be a solar cell, right? So we have a single PN junction. You know the depletion zone. There is an inbuilt electric field at the depletion zone. So if electron hole pair can be created near or inside the depletion zone, they will immediately get separated due to the inbuilt electric field. And if that electron hole, photo-generated electron hole pair come into the external circuits, then we can get the electrical power as well as the voltage due to the potential barrier height at the junction. So this is where the efficiency reduces. That means the most of the electron hole pair that is generated by the light is lost due to the recombination. You know the recombination is the process. So when this electron hole pair generated near the interface, they have to travel this distance to get into to be collected by the electrical contact, and then it flows to the outer circuit. So in this process, most of the electron hole pair gets recombined. Now this recombination is inevitable; you cannot avoid it. So that is why the solar cells are mostly inefficient. The efficiency is quite less. This is the characteristics part of a PN junction solar cell. We have to measure the current voltage relation, that means IV curve upon solar light, and this is the dark IV curve. This is for a single PN junction that you all know, and this red part is the IV curve under illumination of the solar spectrum. So we get current in this direction, in this opposite direction, is negative current. That means the minority carriers contribute to this photocurrents. That is why the current is in the opposite direction. And this VOC is the maximum voltage developed in the junction. So where the current is 0. So that is known as the open circuit voltage. That is the maximum voltage you can get, and this is the short circuit current. That is the maximum current you can get from this. But if it's a power supply, so it must supply the power to your circuit. So you must add some load. So when you are using load, you will get this much of voltage and this much of current. So this is the part that shows that there is a point of maximum power. This is the point of maximum power. That is the voltage into current, and that is the maximum power. Okay. Now the efficiency is basically the how much of the incident light power is being converted into the electrical power. Okay. Now if this fourth quadrant curve, that means VOC into ISC, that means open circuit voltage into short circuit current. If we multiply this, that means we have a rectangular shape. So that is the maximum output you can get from it. But that is not happening. So the maximum output point is here. So this fill factor actually defines how much of the this maximum power output divided by the VOC into ISC. So fill factor is very important. Okay, so fill factor is very important here. And the power conversion efficiency is the total power conversion efficiency. The total input light power is being converted to the electrical power. So you have to consider the total power of the incident light energy. So not all the incident light energy is being used for the power conversion. So it depends on the material you are choosing. It depends on the band gap of the material. The energies which are greater than the band gap of the materials, they are only being converted to the electrical power. So the rest of the energy is being lost basically. So that is another that is one point of view.
Just to understand how the fill factor is calculated.
How
How the fill factor is calculated.
the fill factor is being calculated from this curve. Actually, you have the maximum power point, that is the output, okay, and that is divided by the VOC into ISC. Right? So that will give you the fill factor. And if you multiply it by 100, that will give you the fill factor in percent. Okay. So that is the dilemma. Huh? Solar cell is a power supply. So if we want to increase the current, the voltage reduces. If we want to increase the voltage, the current decreases. Right? So if you want to increase the current, so you just make the band gap lower. So you absorb more energy, more current will produce, but that will reduce the voltage. Okay? But if band gap is increased, the voltage will increase, but it will reduce the current. So optimization of the band gap of the solar spectrum. So which band gap is actually suitable for the maximum power output? There is some theoretical studies by Shockley-Quasar, that is known as the Shockley-Quasar limit. This is for a single heterojunction based calculation where a single PN junction is considered and one electron hole pair per one incoming photon. That is the assumption, and illumination with the unconcentrated light. So if you look at this curve, the efficiency versus band gap. So maximum efficiency as predicted by the study is 33% for optimal band gap of 1.34 electron volt, right? And for silicon-based solar cells, this maximum efficiency has been reported as 29%. But actually, what we see for the silicon modules that we use in our households or in practical applications, they have the efficiency much less than this 29%, around 10 to 14%. So what should be the development strategy? So we have to get more electrical energy out of the device. Now high efficiency with high cost, that may be one strategy. So we need high quality crystalline materials so that the recombinations are less. Okay. Tandem solar cell, that means we have to move from the single junction based solar cell. We can use different band gap materials for multiple junction and use the most of the energy spectrum of the incident light. So in that case, the production cost will be by many folds because we have to make several junctions, and that is the tandem solar cell, and they have a very high efficiency, but they're with high cost. Now, another strategy should be the acceptable efficiency with lower cost. Thin film solar cells in that case is very useful because in thin film we use a very thin layer of materials. So we are using very less amount of materials for thin films. So the materials should have very high absorption coefficient. With very less physical thickness of the material, it must absorb more amount of light to get more number of electron hole pairs. So that light absorption, so that is one of the issue. Obviously, the band gaps are there. And conventional thin film solar cells are amorphous or polycrystalline materials, made of amorphous polycrystalline materials, and organic materials are being used for the solar cell fabrications, but their efficiency are limited, and obviously they can be fabricated very easily and with lower cost. So to make the power from photovoltaics competitive with the fossil fuel technologies, the cost needs to be reduced by a factor 2 to 5. So this is the development.
Advantage of taking this amorphous or polycrystalline.
Not exactly advantage, because that the efficiency will be less than the single crystalline part. Okay. Now the current photovoltaic market is dominated by the crystalline silicon-based solar. That we see the solar panels. Now we don't get silicon as a silicon in our arts class. Okay. So we get as a SiO2 or something. So the processing of the crystalline silicon from that minerals is a costly task. Okay. Another point is that why people are trying to get rid of the silicon. Silicon is indirect band gap material. Okay. So as I told that the electron hole pair generation is the fundamental thing. So for indirect band gap case, phonon is phonon is informed. Okay, so when they tends to recombine, they emits the excess energy is converted to the heat, and that is detrimental for the efficiency. That is why the efficiency is limited to certain, but they are very stable. That is why they are marketable. So when we are switching to the other things like thin film solar cells, so we are developing a very thin layer of films. So they are not so crystalline. They are by nature amorphous. Okay. The only idea is that very less amount of material you can use for this thin film solar cell. And another part is that when you are making a junction at the interface at the depletion region, the electron hole pairs are created. They have to travel less distance, less physical distance to get to the outer circuit. So the probability of recombination gets less. That is somehow the efficiency is increased. That is the idea. Amorphous is direct band. That is another point. Amorphous silicon is direct. So direct band gap material is suitable for the optoelectronic applications because phonon is involved here. So when the transition occurs, the momentum doesn't change. So to make the momentum conservation, we need a phonon. So this is the some generations of the development of the solar cell. If you say this time scale is roughly mentioned. This is not very you don't take it seriously, but you know that single crystalline silicon wafer is the first generation of solar cells that we know about, and the second generation of solar cell is the thin film solar cell, and amorphous silicon as well as the cadmium telluride. In fact, cadmium telluride is one of the most efficient solar cell, thin film solar cell in today's solar cell PV technologies. In India, in Chennai, there is a startup company. They are fabricating the cadmium telluride based thin film solar cells for multiple applications. And third generation solar cells, they are trying. There is an immense try to advance increase the efficiency of the thin film solar cell. And this is a very complex material that is copper, indium, gallium selenide. So that means CIDS popularly known, and they have shown extremely efficiency, extremely high efficiency when used as the solar cell materials. And obviously, there are some emerging technologies that are being used right now. Perovskite solar cell, most of you have heard of the perovskite material. They're really going to be the game changer in the future because their efficiency has exceeded the theoretical efficiency set by the shock deposit. But the problem with the perovskite material is their stability. They degrade very fastly in the open ambience. So that is the actually problem. But the efficiency is very high for the perovskite material. And obviously, the organic photovoltaics, quantum dot, dye synthesis solar cell, their efficiencies are moderate, but they can be fabricated very easily, and that is why people are very interested about that, because the cost can be reduced by some point. Cadmium-free materials we want because cadmium is not good for the environment. Okay, and CIDS also toxic. Yeah. So the technology we want to develop in near future must be environment friendly. We are nowadays so dependent on technology. We don't get rid of that, but everything is technology. But we have to keep in mind about the environment issues right now. So the cadmium telluride is efficient, but cadmium is not a good for environment. At a similar fashion, the copper indium gallium selenide, that is the most efficient material for the thin solar cell. But the presence of indium and gallium is not good for the environment. So people are trying to fabricate different materials. That we will talk today, that is CZTS. So in CZTS, basically, the indium and gallium being replaced by the zinc and tin. So they are earth abundant, at the same time, they are not toxic for the environment. That's the issue. So these are the emerging technologies that means these are the different idea of getting efficient power from the incident light. Now, here is the chart that shows the reported efficiency of different kinds of solar cell devices certified by the NRPL, and you know that the efficiency are getting increased with time. Okay. So definitely, as I mentioned, the silicon is being the most of the present photovoltaic market is dominated by the crystalline silicon-based wafer, and major concern is less power conversion efficiency with high processing cost that I already discussed, and large amount of materials are required because you want some silicon wafer you have to get. So possible solution may be thin solar cell. So you need a very thin amount of material. Junction of thin layers of material with very high absorption coefficients, less amount of materials are required, cost effective obviously, and there is a possibility of transparent and flexible cells with better integration possibilities. So you know that silicon solar cell or solar panels, you have to put it on your rooftop, and a lot of space are required. So you can integrate the solar, a thin layer of coating on your wall of the house, and that can generate the power. So that is possible with the thin layer of coating. So that may not be so efficient, but that is technologically important. Transparent in two sense, transparent means the band gaps are higher, right? Band gap higher means it mostly the sunlight, in the visible light, it passes the light, but it absorbs the higher energies. Okay, so it is not so efficient for the solar light, but the higher portion of the solar light, and if a UV part or something, so you will get very less amount of current, or efficiency should be less. But if you are coating your window with some transparent coating, that can give you some certain extent of power. Okay, so that is it. Okay, energy losses I said, why the efficiencies are so less, that should need another talk actually, why the efficiency of the solar cells or the devices are so less. That is because of the recombination is the primary concern. Okay, now not only the recombination, so you have the contact. So from the solar cell devices, you have to collect the charges through the contact. So at the interface, there is some trap space that trap the charges and reduce the current at all. So the heterojunction is another idea. So in heterojunction, basically 2 layers are used. One layer is transparent, that is known as the window layer. So transparent means the band gap is higher. So it transmit all the incident solar light. Okay, and another layer is low band gap material, that is known as the absorber layer. So their band gaps are less, so they absorb the incident sunlight. Right? So the light is actually entering the device through the window layer. Okay, So this is N-type window layer and the P-type absorber. And above that there is a transparent conducting oxide that acts as the electron. So if light entering through this direction, the light transmitted through this window layer because that is transparent and falls on the absorber layer. Now what is the advantage of this kind of structure? The electron hole pair, that means the light reaches here at the junction, physical junction, and the depletion region is here at the physical junction. So the electron hole pair basically generates here. Okay. Now if you use both the silicon, N-type and P-type silicon, the light would not enter into the junction, but reach the junction. So this is a transparent layer that is called the window layer. So the light transmits through the window and goes to the absorber junction. So it actually electron hole pair generates at the interface where the inbuilt electric fields are there. So the possibility of separation is higher, right? So this is one kind of structure where the we only thin films are deposited on a substrate. Okay, so substrate, then P-type absorber layer with a lower band gap material, and then a transparent layer with a higher band gap material, and then there is a transparent conducting oxide, and light is falling from this side. And there is another configuration that is the superstate configuration. Superstate configuration means the window layer, absorber layer, and contacts are there, but first we deposit the window layer on the substrate. Okay. So normally the window layer is used as a high band gap materials like zinc oxides and all those things. So they are the oxide materials. They are not very stable in amperage. So if the light enters the junction through the substrate, so they are being protected to the ambient. So stability is more here in this case. So, but obviously for the superstate configuration, the light getting reflected, and in that case the energy loss is more. So efficiency is less here, but the stability is much higher. So we have again a problem. Okay, so some of the emerging technologies that we are talking about. So not, I mean, the simple PN junction based thin film solar cells are there. This is the dye synthesized solar cell that work as a in the mechanism of a photoelectrochemical cell. So we have anode and cathode. So anode is basically a high band gap transparent semiconducting material coated with the dye molecules. Okay. So light falling from this side, dye molecules are getting excited. So that electron is going to the higher energy state, and the electrons is being transferred to the conduction band of the anode, that is semiconducting material, and they get transferred to the outer circuit. And this is the cathode, and there is a redox element, that is iodide and triiodide, and these dye molecules get electron from this redox and it is generated, and again the process continues. So this is how we get the current and voltage in this direction. So the cost-effective obviously and easy fabrication, better integration possibility. You can see the Swiss State Convention Center, the wall of the Swiss State Convention Center is coated with the DSSC part, and obviously the stability is a major concern because the electrolyte solutions are used here. So the stability of the electrolyte solution is a major concern here, and efficiency are limited. Organic excited solar cell. This is another idea of getting the current out of the incident light. So in this absorber, in this sensitizer, light produces electron hole pair, but they are not free electrons and free holes. They are bound together by some Coulombic interaction that is known as the excitons. And in this organic layer, the excitons can diffuse to some extent, and when they diffuse to the interface of donor and acceptor, at the interface, due to the inbuilt electric field, they get dissociated, and the hole transported this side to the transparent anode, and electron get transported to the cathode, and we can get the current. So again, the efficiency is limited, stability is an issue here. Organic materials are being used, but this is organic solar panel you are seeing here. Quantum dot solar cell. The quantum dot is the nanostructure we mentioned. The light is, I mean, in the quantum dot layer, the electron hole pairs are generated and they are being transported by the to the outer circuit, and this size tunable band gaps, the quantum dot, depending on the size of the quantum dots, the band gap can be tuned, and accordingly the efficiency can be tuned. So light absorption is very high here, and low cost production is possible, but again the efficiency is a concern, as well as the you can see the quantum dots are lead sulfide, cadmium sulfides, and all those things. So the environmental toxicity concerns are there. Perovskite is definitely the big issue nowadays, and they have very high efficiency, as I mentioned. That perovskite is basically a general formula as ABH3, where A is a cation, B is also a cation, and H is a halide. And because of the particular structure and properties of the perovskite, they have very high efficiency. The electronic, the charge mobility is very high, so absorption coefficient is also very high. They can be fabricated also very easily, but the problem is again the stability and durability and toxicity is also a concern. So thin films are the only possible right now. Thin films are only has a hope to be marketable right now. So as I mentioned earlier, the most efficient thin film solar cells are being made of copper indium gallium dioxide and cadmium telluride. But the presence of indium and gallium and cadmium and telluride and in cadmium, they make this presence of rare and toxic elements. So we have to look for another kind of it. This is the crystalloid structure material, that is indium and gallium in the CIGS has been replaced by zinc and tin. So they have the similar kind of band gap optical properties and similar. Their presence of earth abundant and non-toxic elements make them most promising for the solar cell applications. And their efficiencies, highest recorded efficiency is like 15%. This is the lab scale efficiency, So the efficiency, actual efficiency should be very less when you are using it in the ambient conditions. So if the material is suitable for the requirement of green energy technology at a modest cost. This is our work. We try to develop a super-straight solar cell using the zinc oxide nanowires and CZTS heterojunction with a buffer layer, that is the zinc sulfide. Buffer layer actually tried to improve the junction quality. It has some roles in the device fabrication. The interface defects it reduces actually. So, and using the zinc oxide nanowire as the nanowire, in case of zinc oxide nanowire, the electron can be transported easily through the axis of the nanowire, and that you can get more current here. So this is the various synthesis techniques. Vacuum-based techniques are high processing cost, and non-vacuum-based techniques are easier, simple, and low-cost methods. There is a conventional sol gel chemical method to deposit thin films. And here's the zinc oxide nanowire synthesis techniques. It's a two-step process. Zinc oxide seed layers are deposited first on the substrate, and the zinc oxide seed layers are dipped into a chemical solution to grow the zinc oxide nanowires along the C-axis. Okay, so here is the result. This is the AFM picture of the seed layer, and this is the particle blind zinc oxide nanowires. This is the top view. It shows some hexagonal structure here, TM of the zinc oxide nanowires, and this is the X-ray diffraction pattern. Okay. And the time is very short. This is a conventional optical transmitter spectra. From the optical transmitter spectra, you can estimate the optical band gap, because can direct band gap, and the band gap is about 3.24 electron volt. So this is transparent material and can be used as the window layer for solar cell applications. So a very thin layer of zinc sulfide coated on the zinc oxide nanowire. These are the microscopic studies, and on top of that, we synthesize the CZTS in chemical route, right? Now we optimize this synthesis process because we have 4 elements: copper, zinc, tin, sulfur, and to get the stoichiometry of the film is very here, but we optimize this, and after the deposition, the films are heated in the sulfur or selenization vapor to get the stoichiometry, but we avoided that part and still we get the result. This is the scanning electron microscope results. X-ray diffraction and Raman studies confirm the formation of the crystal structure of the films we deposited. Okay. So this is composition, optical absorption, the band gap shows 1.345, and this is impedance spectroscope study. Okay, so the solar cell characteristic that we got from is, we can find that the power conversion efficiency is very less. But if you compare with the other superstate cell structure, this is comparable, and the field factor is very less. That is the point. So in this work, actually, we discuss why the power conversion efficiency of the solar this kind of structure is less because of the effect of shunt and series resistance are there. Now, the challenge with CZTS is why the CZTS-based devices are efficiencies are less because of the intrinsic defects present in the fields. Defects play a major role to determine the device efficiencies. Okay. Now, cation substitution strategy, that is one recent strategy to reduce the point defects or vacancies, and we can substitute partially or fully the copper or zinc or tin, the cations, by some similar ionic radius materials with higher activation energy, so that the probability of forming the defects is less. At the same time, it increases the efficiency of the devices. Now, this work we have done a solution process application of a heterojunction, single heterojunction, TIO and CZTS based, and we have studied the photodetection characteristics under the solar illumination. This is the self-powered photodetector. So junction is there, and just upon illumination of the solar light, we get the photocurrent. So this is the photo response parts of the devices, and this is for the CZTS TIO heterojunction, and the current increases significantly with the heterojunction when you partially substituted the copper with the silver. Okay, so this work is in progress, and we are not going in details. We have started for different range of illumination, I mean from red, UV to NIR regions, and for a broad range of electromagnetic spectrum, we have got the good photodetection properties for this heterojunction. So, okay, I'll stop here. Intentionally, I have avoided all kind of theoretical part because most of the people are here from theoretical background. But you must remember that the technological revolution that happened today is because of the theoretical development, right? Now, this kind of theory is quite complicated. Some of you have talked about the DFT, density functional theory, that is the most studied theory. Simulations like FDTD are there. So people are working on that. We are also using the DFT for the material modeling and the property application. So I stop here. I mean, this is the very brief overview of the different kind of technologies, solar cell technologies that is emerging, and the people are facing trying to solve the challenges we have with the materials, the junction, and the device you make must be the environment friendly and cost effective to meet the requirement of the green energy technology policy. So here the people in my group, my students are working at Jadavpur University, are trying to set up a lab there. The source of funding from the SCRB and Government of India, DSP FIST, and West Bengal DST.
So I think we have explored our possibility of using solar energy in our daily life. So now I quickly pick up 3 questions maximum from the audience. Yeah.
Thank you for the very nice overview. Probably this part I missed or misunderstood. So just to clarify, when you introduced your CZTS solar cells, and you mentioned about 14.5% efficiency, but was the end of that, was the conclusion you mentioned. So how these two are different? Is it structurally different? Or?
Yeah, the 14.5%, that is the maximum input efficiency in the CZTS sources. So normally the solar cell structure uses the substrate configuration. Okay. That means the CZTS layer is on the substrate, and on top of that we have the buffer layer and window layer. The window layers are basically the transparent and high bandgap semiconducting layers, mostly oxide semiconductors. So oxide semiconductors, so you have to enter the light from the window layer. So the oxide semiconductors are exposed to the environment. So you know that zinc oxide, they are not very stable when you expose to the ambience, right? So that is a problem for the substrate configuration. Now, when we go to the superstate configuration, so we have the substrate, it's a glass or quartz, whatever we make, then you deposit the zinc oxide or high bandgap material, and then the absorber layer. So absorber layers are more stable to bandgap, and you are exposing and light is entering through the substrate. So the zinc oxide or the high bandgap materials are not getting exposed to the environment. So in case of stability issue, the superstate structure is more efficient and more usable actually.
That you mentioned that there is some optimization between stability and efficiency.
But the problem is the less efficiency. You know, the efficiency is extremely less. When we are going to the substrate configuration, the efficiency is greater than 10%. But when you're going to the superstate configuration, the efficiency is highly 3 to 5%.
So the reported efficiency itself is less,
Very low.
much less.
So people are trying to sort out this issue. Why the efficiency is so less? One of the problems is that when the light is getting reflected, a part of the light is getting reflected from the substrate surface. We have to choose the substrate accordingly so the most of the light should enter the device. Okay, another problem is that the substrate and then the material you are depositing. At the interface, there is a lattice mismatch, and that creates a interface defect space. And they act as the trap center for the charge carriers. So they reduce the detriment for the device application. Right? So the suitable choice of the substrate should be one issue. Another is the band alignment should be such that interface defects should be less. The electrons, the charge carriers should not get recombined at the interface due to the defect space. So the mostly people are concentrating on the superstate structure. We are also trying to develop the superstate structure. Although the efficiencies are very low, but if you think about the marketable solar cell, so it has to be stable in ambient condition. That reported 14% is in lab scale. That means in protected environment, it is measured and certified, and that is the highest.
What is the effective cell area when you repose this efficiency?
Okay, the effective cell area is the order of centimeter square. 1 centimeter.
Thank you.
Any other question, please?
Like this was, you have mentioned previously that the photovoltaics efficiency was set before. But while getting the efficiency is shorter, like from what the from power. So what was the
For the perovskite?
for the perovskite?
Okay.
So what was the explanation behind after that results of what why
Okay.
that such?
Yeah. The theoretical limit that was set, the software qualification, that was based on a single junction. So that was based on a single junction. And there's some obviously it's a theoretical development, there's some assumptions and all those things. But when we're talking about the perovskite solar cells, they are not based on the junction. They are not based on the semiconductor junction. Because the perovskite structure, due to the perovskite material, due to the structure, it has its inbuilt electric field. So what happens there, the electron pair generates as a pair. That means the excitons are generated. Now the excitons get easily dissociated into the charge carriers, right? And they are efficiently transported through the material because of the ion conducting barrier. So the theory developed based on the semiconductor junctions and the mechanism of the perovskites are completely different. That is not applicable here. So what I mentioned is that that limit set by the theory has And the perovskite you can integrate with the other materials also. So you can, so that you can use multiple number of layers to increase the efficiency, to increase the more number of photons to contribute to the electrovoltaic generation, to absorb the more sunlight. But that would make the processing cost higher. That I mentioned, that strategy you can take. Yeah, you will develop some devices is very high. You should not bother about the cost. That is one strategy. But what is useful to make the device moderate efficiency, but the cost must be lower. Otherwise, it would not compete with the commercial, I mean, the conventional sources, I mean, energy sources like fossil fuels. And
Okay. One question is there.
Is there any reason, I don't know, what you want to say, I'm probably more, is there any reason that this
this means no, I have not got 40%. I have got very less, around 1.1%.
And
And in that paper, we have only discussed why the efficiencies are so less. That is the one part of the research work we did. So you get very high efficiency, there is then no need to do research at all. So actually that paper, in that paper, we actually discussed what are the problems here, why that we are getting the so less efficiency. So there is no baseline. You try to improve your device, okay. So if you get the bad results, you go back to your theories, you go back to your basic knowledge of physics, chemistry, whatever you know, and try to model it, try to give an explanation for this. That is a good research what I do. So it's not about getting the high efficiency devices all the time. Okay?
so I have one query. So is there any aging effect? I mean, how efficiency changing with time?
Absolutely. Engineering means if you keep it in ambience, the device gets the efficiencies decreases with time. What is the main problem with the perovskite? Perovskite's efficiency is very high, but if you just measure in the next day, the efficiency drops to because it gets degrade with time. So that is also true for all kind of devices. So the stability, what Professor Nayak mentioned, the stability is the major concern for the solar cell devices people are working out now. The certified recorded efficiencies are above 20%. Yeah, so that is quite high. That for silicon wafer-based solar cell that you see in the market, the efficiency is more or less 10 to 15%. So in lab scale, people have developed the solar cell devices with efficiency more than 25%, 30%. That is important. That I showed the solar cell chart, an efficiency chart. But why it's not marketable? The stability issue is the major concern till now. But one thing I want to mention here, the perovskite is going to be the game changer. Few companies have actually they have demanded that they have solved the stability issues, and it is going to be marketable within 2-3 years. But there is no data till now. And the data is a secret. So as a scientist, we still don't believe it. But I think they have got it. They have done it. Okay. So they are the companies of the US-based companies. They have demanded that it's going to be marketable within 2-3 years. Okay. So it's going to be a big issue.
In the stability issue, still silicon is a golden metal.
And no doubt, silicon is still the dominating the photovoltaic market.
So, thank you very much. Gift. So thank you, sir.
Thank you, Doctor. Thank you, Dr. Gayen and Professor Naik. Now let us move to the second oral presentation session of this day. This session will be chaired by Turni Bishwas, a PG2 student of Department of Physics, Presidency University. So over to you.
Thank you, Shavni. Good afternoon, everyone. I am Turni Bishwas. Welcome to the fourth and final oral presentation session of our conference. We have 5 speakers lined up for this. Please note that each presentation will be followed by a 3-minute question and answer session, and the speakers are requested to conclude their talks within 12 minutes. I'll give them a reminder at a 10-minute mark. To the audience, kindly refrain from asking questions during the presentations as it may disrupt the speaker and consume more time. Please save your questions for the designated question and answer session. With that, let's proceed to our first speaker of this session, Dr. Amitabh Moitro, Faculty of Department of Physics, Raidighi College.
Thank you, Turni. Thank you so much. A very good afternoon to all of you. Before I start my presentation, a few slides on this interfacial dynamics during melting of nickel-coated aluminum nanoparticles. Few words I would like to appreciate of this institution's students. I sincerely grateful and as a wow factor for all the students and their dedication and enthusiasm for this organization. Thank you so much. All right, now in this talk, so the single crystal nanoparticle melting is kind of very old, and I think it's from 2008 paper. I pick up these pictures for tungsten nanoparticle melting. And during that time, or even before that, you would be able to see that lots of phenomenological model on predicting the melting temperature for different kinds of size of these nanoparticles. The interesting fact is that before the melting, before these nanoparticles actually got melt, the surface of these, the surface atoms actually got pre-molten, and that's known as pre-melting phenomena. And the displacement of the displacement vectors of these atoms are being shown over here. Now this is single crystal nanoparticle, but if you go to a bicrystalline nanoparticle, what I'm trying to project over here is a nickel-coated aluminum nanoparticles. There are two different things. One, aluminum is very lighter than nickel. And two, nickel melting temperature is far higher than aluminum itself. So these two mismatches actually give a rise to several technological applications of this nickel-coated aluminum nanoparticles, such as high temperature structural materials, tribological application, fuel additive, so many things. So the way we develop it is atomistic simulations. So we have a nickel nanoparticle, and then we remove chunk of atoms from the center of it and then put aluminum into it. When we do that, both of them, aluminum and nickel, both of them are FCC system, and the orientation of both the FCC system remains same. It's just coloring of these two different materials, aluminum and nickel. And here, once we do that, we kind of relax the system so that it can come to a conjugate gauge gradient relaxation. And this is what you see, that there are so many lower or lowest energy structure even at the interface, which is kind of a novel thing, because if you see there's supposed to be a mismatch of lattice between the aluminum and nickel, but it does not happen over here. And there are so many patch-like structure which says that there are stable structure of aluminum nickel interface. And after a vivid observation, we figured out that there are actually so many nickel 3 aluminide structure that forms at the interface of this. Now, so many nanoparticles that we develop, the shell thickness is given, the number of atoms at the shell, the core atoms and the core thickness they are given. The thing is that you can see that there are so many atoms that we are modeling. And of course, density functional theory or those kinds of given theory will not be able to predict the situation over here. So we have to go to the semi-empirical atomistic model. The basic idea of this kind of model started from textbook like Lennard-Jones potential or Morse potential over here. But both those potential long ago they started, initiated, but they failed to predict certain material properties. They are very good when you try to model a perfect system, perfect lattice, perfect crystal. But for example, this Lennard-Jones potential, they fail to predict the material when you have a surface. So the surface atoms actually evaporate. The Morse potential, if you try to make a nanoparticle kind of structure or a dislocation into it, then it disintegrates. So these kind of problems are there with the classical potential. So with this around 90s, late 80s actually, 88 or 89, embedded atom method evolved. The key idea of this embedded atom method is that how much energy is needed for one atom to be inserted in a sea of atoms. So that is the key idea. Little bit mathematics over here is basically to predict the energy of the whole system is half of phi. Phi is the energy or interaction potential between the atoms I and J, and half comes because you are basically having it twice when you sum over all the atoms. And certain embedding function over here is Fi, and F is a function of the electron density and atomic number. These rho are given taken from, classically it's taken from the DFT calculations, but later on, honestly, frankly, these are basically a Legendre polynomial, and from there you basically fit. I'm not going to the detail of this semi-empirical potential, but typically the idea of this definition or the application of this semi-empirical potential, that when we develop such a potential, we drag material parameters from experimental value or from density functional theory value. So these values are typically your target parameters. And with these target parameters, you develop the model, and then you try to study a long-range defect problems. So essentially, the performance is dependent on the property of the material and the properties on microstructure and processing. So back to this atomistic configuration at different temperatures, what you see is, seeing is believing. So what you see is the melting happens or begins at the interface of a nickel-coated aluminum nanoparticle. And as you keep on increasing this temperature, it melts at first the aluminum core and then nickel. The red atoms over here you see is basically, we do here a common neighbor analysis, and we run LAMPS. LAMPS is basically a Sandia National Lab molecular dynamics code. And we visualize using Stokowski's OVITO, open visualization tool. And this color coding is essentially with the green atoms are FCC atoms, and the white atoms are essentially which does not belong to any FCC, BCC, or HCP atoms. The HCP atoms over here are the red atoms, and it can be confirmed that these HCP atoms are essentially the stacking faults which are beginning at the surface of this nickel and then come close to the interface of this nickel-coated aluminum nanoparticle. Not only limiting to the observation of the atomistic structure, we also calculated the energy evolution and the corresponding specific heat or the derivative of this energy. There are three different stories at the left panel, but the first right-hand panel, it's basically the specific heat and derivative of the energy. And as you can see, we divide it by C0. C0 is the classical canonical vibrational and rotational part of specific heat. And the A part over here, which is zoomed up over as an A, and this B is over here is zoomed in. But in the left panel, there are two different stories. So for the upper panel, this is the aluminum core. A typical the behavior is as you keep on increasing the temperature, the energy will be increasing, and there will be a sudden jump which will predict the melting temperature. That happens over here for aluminum and over here for nickel. So that is the first story. The second story is, even if you go to a higher temperature, then these different nanoparticles, suddenly the energy drops off. A peculiar phenomena. And this peculiar phenomena happens almost for all different nanoparticles. This happens because aluminum and nickel, when they interdiffuse with each other, it's basically an exothermic reaction. So they go to a lower energy structure. The third story of this is that you see that, well, this happens for all the aluminum core, but for the nickel, it does not happen except for this 2 nanometer cell thickness. This is because as you keep on increasing the number of cell atoms or the thickness of the shell, there are more number of nickel atoms, and those parts, the fraction of nickel atoms is not pronounced over here, that the interdiffusion mechanism of the exothermic reaction process. So this is the evolution of energy and specific heat. Next, we do coordinate number analysis, and coordination number is essentially is a kind of geometrical number through which you can identify the shape of the particle and size of the particle and so many other things. But since both the aluminum and nickel are FCC structure, so their coordination number is 12. And for the different cases, we figured out that the coordination number 12 start to reduce at different temperature at 40, which is basically at the interface of aluminum nickel interface. Yes, thank you. So this is the coordination number analysis. And finally, this Lindemann index. This Lindemann index, again, another method through which we kind of calculate the melting temperature of this nanoparticle. And essentially, the physical meaning of this Lindemann index is how much fluctuation do we have within the atoms. If it is more than 20% for a metallic system, then we call the melting happen. So with this, we again say that the melting actually begins or initiates at the interface of aluminum nickel nanoparticles. The take-home message is basically the bimetallic nanoparticles have lots of interesting properties for the engineering applications. My colleagues and my collaborators at present. Thank you so much for your attention. Yes.
So you are measuring the specific heat just from the derivative of energy?
Yes.
Okay, so can you show the slide? So if the temperature increases and the correspondingly energy decreases, the specific heat should be negative in the case.
Yes. So that's been shadowed over here. This is for aluminum. This is, this part where you are talking about for this nickel. Yes. So, yeah,
So if you are the y-axis scales is positive.
Yes.
dEdt should be negative.
Yeah, I guess. Yes, good point. Good point. I don't remember right now what I did.
Maybe this is absolute value anyway. So what is this peak corresponding to this peak? What the CV call? Any transition? Any?
No, nothing. It's just the value. It does not particularly correspond to anything, or at least we were not focusing on any meaning particularly from this CV by C0. We were trying to see whether it happens at the interface or not. Our objective was that.
You are not going to conclude that there is some kind of phase transition is going on.
Yeah, melting is phase transition.
That is the melting transition.
Yeah, melting. Melting is
that,
phase
that is
transition.
the significance of the
Yeah.
peak of
So basically this peak corresponds to the melting occurs at that particular temperature for nickel. And this happens for aluminum. Huh?
Nickel melting point is very high.
Very high. It's like 1500, close to 1500 centigrade. And aluminum is 660 degrees centigrade. But I think, yeah, I took the absolute value. I don't recall right now. Okay, thank you so much.
Thank you, Dr. Moitro. Let us move to our next speaker, Shubhashish Sheth, a PhD student from IIT Kharagpur.
Good afternoon, everybody. I will talk about the fluctuation-induced conductivity in GDBC superconductor, and finally, I will reveal how this BCS phase is coming to the samples from the BEC state. So, before going to the topic, I will discuss basic superconductivity. So, superconductivity is first observed in mercury by Kamerlingh Owens in 1911, and it has some peculiar properties like below some transition temperature Tc. Its sample shows the perfectly conducting, and it will expel all the magnetic fields inside the samples. That means perfect diamagnetic, and also some of the superconducting samples can allow to penetrate the magnetic field inside the samples, but in a quantized way. So after discovering the superconductor in mercury, so many research have been done on this field, and there are so many superconductors are there. But I am only focused on these cupid-based superconductors. And the cupid-based superconductors has the property, it has a layer structure. In the layer structure, there are two types of blocks. One is called the active blocks, another is called the charge reservoirs. And charge reservoir is the block where the charge is created in that block, and then the charge is going to these active blocks, and finally these active blocks participate in the conductions. And the active blocks is based on the copper oxide planes, and this is the generic formula of the cupid-based superconductor. And depending upon the doping concentration in the superconducting samples, the samples might be in the superconducting dome or in the antiferromagnetic insulator. So now I will move to my talk. The roadmap of my talk is like this. First, I will discuss about the motivation of my for choosing these GD-based cupids, and then I will talk about the motivation to study this type of analysis. Then I will discuss about the structural property of my samples, and I will finally discuss the fluctuations conductivity present and the pseudograph study, and I will end up my talk with some summarizations. So the sample is basically the GD-based cupids. The mother compound of this type of family is the YBCO. It is oil-bound samples. Many groups have studied these YBCO cupids, but in our cases we have replaced the yttrium by GD3 plus ion, and it is known to us that GD3 plus ion has the magnetic moment, effective magnetic moment 7.97 MeV, and it has the antiferromagnetic temperatures 2.24 Kelvin. And it is also known to us that magnetic ion cannot be present in the superconducting sample. They are rival to each other. But still, if you see the magnetic hysteresis loop, we have the magnetic hysteresis loop just same as the superconducting samples. But if we see very closely that our GDVCO sample has the tilted magnetic hysteresis loop compared to the YVCO samples, and this tilted nature has been observed due to the paramagnetic moment present in the GDVCO samples. So that is why we have selected these samples, these GDVCO cupids, because to understand if there is any effect of the magnetic moment to other superconducting properties or not. And Then we have studied the electrical resistivity to ensure the superconducting properties of the samples. So we have done this resistivity measurement with respect to a temperature in presence of magnetic fields, and we have identified different characteristic temperatures like TC onset, TC AMF, and TC zero from these derivative plots. And one thing is noticeable that whether when the sample is in the normal state, still there is a deviation from the rho t in the normal state when the sample is already in the normal state. So that deviations present in the samples due to the fluctuations present in the samples, and the superconducting fluctuations is there because the creation of Cooper pairs in the normal state and the interaction with the remnant electrons are the main cause of the superconducting fluctuations, and that is why at certain temperature T star in this plot, the fluctuation is there, and effectively the conductivity has been increases before the TC onset. And also literature says that the strongly coupled bosons are formed at T equals to T star, but eventually if we close to the TC wave, the fluctuating Cooper pairs are there. So that means there is some evolution from the strongly coupled bosons to the fluctuating Cooper pair. So we want to study that how they are evolved in the samples. So we have prepared the samples using this TSMG method to overcome the grain boundary problems. So this is we have done the XRT analysis, and from the XRT it has been shown that the sample is highly oriented along C-axis, and at 2 theta equals 30 degrees, some smaller peaks are there due to this presence of GD211 phase, which is present in the buffer pellet. And also we have identified the room temperature structure of my sample is orthorhombic, having space group PMM. And from this XRT analysis, we have identified the C-axis parameter. And from that empirical relations, we have identified the oxygen's deficiency present in the samples, which is important for any type of Cubic superconductor. So that delta is 0.4 for my samples. And then we have studied the fluctuation conductivity in the samples using this formalism. The excess conductivity or fluctuation in this conductivity is defined by delta sigma, which follows these equations. And according to the AL model, the excess conductivity follow the power law relations with the reduced temperature. And this exponent has different dependencies like critical exponent, coherence for coherence length, dynamic exponent, all these things, dimensionality. And depending on this lambda, the fluctuation in the samples may be in the critical field region or in the mean field or in the short wave region. And if we see that in the mean field region, the sample the fluctuations may be in 3 dimensions or 2 dimensions in 1 dimensions. So let me show you that in our samples what type of fluctuations we have observed. So to understand this, we have first plotted the data, and from there we have fitted the equations, and from there we have found that we have mainly 3 regions: CFR, MFR, and SWR. And in the mean field regions, we have only 2 types of 2-dimensional fluctuations. Only 3 dimensional, and then these are 2 dimensions. No 1D fluctuations is present in my samples, and all the exponents are basically matched with the theoretical value. And if we see that in the mean field region, the width of the 2D region is greater than the 3D region, which suggests that the Cooper pairs are very much confined in the copper oxide plane. And also one can say that one can identify the interlayer coupling strength of these active layers that can be identified from these equations. And from this model, we have identified the J value for different magnetic fields, and as the J value is very less than unity, so one can say that the interlayer coupling between these 2 active layers are very weak coupling. So we have also studied the C-axis coherence length with the variation of magnetic field, although it is very less dependent on the magnetic field. And also we have studied this Ginsburg number, because Ginsburg numbers certify that whether the fluctuation study in the sample is significant or not. So in the pure superconductor or type 1 superconductor, the Ginsburg number is very less, 10 to the power minus 12 or minus 16 order. But in our cases, we have calculated the GI number by these equations, fluctuations theory, And we have found that the GI number is more or less unaffected with the magnetic field, but they are not that much less. So what we have studied in our sample is significant. And also from these, all the temperatures, intersecting temperatures, we have successfully draw a phase diagram suggesting that the in between the short wave region and the coherent superconducting region, there is a paracoherent state where fluctuation study can be done. And also we have seen that with the increasing magnetic field, the TCMF minus TC0 increases, which suggests that the formation of weak Josephson vortices by the magnetic field. Okay. So now we will go to the pseudograph study, and that formalism is like this. This can be done also from the fluctuation study. That's why we have done these things and try to understand the evolution process. So in these equations, we have in the numerator term two terms are there. This 1 minus T by T star basically defines the number of tightly bound bosons formed at T less than equals to T star, whereas the exponential term takes care of the dynamics of the local plus destructions at T approaches to TCMF. So to understand this pseudograph parameter, there is delta star T, we need two constant. One is called A4, another is called this IC0 star. So for this, we have to fit this data in the whole region, and from there we have extracted the A4 parameter. And for this IC0 term, it has been already observed that T greater than T2D SW, the excess conductivity follows this type of relations. So from there, we have compute this epsilon C0 star, and finally all these parameters put it in these equations, and we get the pseudograph nature with the variation of temperature for different magnetic field. So this is the plots for various magnetic fields. So all the plots looks very same. So we have, as I have discussed earlier, that we have the motivation whether magnetic moment of GD3 plus has any contribution to the superconducting samples or superconducting properties or not. So it has at least in the electrical property, it has no impact. So that is why we have similar kind of graphs. Only we have observed that with the increasing magnetic field, all the characteristic temperature has been shifted towards the lower temperature, which is very usual. So, but one thing we have found from this study is that how the strongly coupled bosons are transformed to these Cooper pairs, fluctuating Cooper pairs, that can be studied from this analysis, and that has been done from this pseudograph analysis, and we have tried to construct a phase diagram. At T equals to T star, only strongly coupled bosons are there, which obey the Bose-Einstein condensational theory. But as we decrease the temperature and cross in this limit T2D SW to 2T pair, some of the local pairs still exist, but the number decreases very rapidly because they try to initiate to pair up, and some local pairs become the fluctuating Cooper pairs. And as we decrease the temperature and below T2D SW, all the local pairs transform to the weakly transfer to the Cooper pair. So that is the evolution process of these strongly coupled bosons to the fluctuating Cooper pairs inside the samples. And also we have estimate the size of the local pairs above which the local pairs cannot exist in the samples. So that becomes the Cooper pairs, and that size we have estimated as 28 angstrom. And from this analogy, one can say that below TC0, when the super sample is already in the superconducting state, but still there is a crossover from BCS to BEC state, and that temperature we have found 45 Kelvin, and eventually we have seen that at that temperature the critical current density increases very rapidly at that temperature. So in summary, we can say that from the fluctuation study, we have identified the different paracoherent state and their dependency with the magnetic field. We have seen that the Cooper pairs are very much confined in the copper oxide plane because the width of 2D region is greater than the 3D region. And also coupling strength is very weak, as the J value is less than unity, and also the fluctuation phenomena is significant because J value is not very less. And from the pseudograph analysis, we have constructed a phase diagram how these Cooper pairs evolve from the strongly coupled bosons, and also we have estimated the critical size 28 angstrom for my samples. And finally, I would acknowledge my supervisors, my collaborator, and my lab mates for various helps in many situations. and that's why I will end up my talk. Thank you.
Now we can have one or two questions.
So what is the source of fluctuation?
Actually the source of fluctuation is basically in the normal state. We first we believe that there is the changes is very abrupt. So we have the electron in the normal state, but in the superconducting state we have the Cooper pairs. The Cooper pairs, but this is not so abrupt. So in the normal state, some of the electrons they try to pair up, and some Cooper pairs are present in the normal state, but they are not phase coherent. So that's why the interaction that local pairs with the Cooper pairs are the main cause of this superconducting fluctuation present in the very close to TC, but in the normal state.
So this fluctuation is favorable for transition temperature.
Fluctuations is present before this TCMF, just higher than the TCMF. It has no impact below this TCMF. Because below the TCMF, we have the coherent superconducting state, no fluctuations as there, no local pairs or no boson, no state. The only Cooper pairs are present in the samples. So all these things are happened very close to TCMF, but above TCMF. Paracoherent state, as I have said earlier, that we have the some Cooper pairs are there, but they are not phase coherent. That's why the conductivity is decreases in the samples just above the TCMF, but we have not reached the coherent superconducting state. So that means some coherence already started inside the samples before reaching the superconducting state, but they are not completely coherent. That's why we have said that this is the paracoherent state. And
We do not have any questions. Thank you so much, Mr. Shi. Next, quickly moving to our next speaker, Deep Mondol, a senior research fellow from Rajabaja Science College.
Thank you to the organizers for allowing me to present my work here. So I work in Department of Physics, University of Calcutta, under Professor Devnarayan Jana. And today I will talk about one of our recent publications, which is the functionalized two-dimensional carbon nitride monolayers, which is found to be a zero topological insulator and essentially made of non-toxic and earth-abundant elements. So this is the outline of my talk. First, I will motivate the reason behind our work, and then I will propose the material and the underlying electronic structure and the non-trivial topologies of the 2D sheet and the 1D nanoribbons and some future prospect, and then we'll conclude the lecture. So considering the successful synthesis of graphene in 2004, the 2D materials has gone leaps and bounds. So the scientists all over the world have tried to come up with different distinct morphologies of 2D materials and tried to synthesis and theoretically propose them. And one of the special family of systems is the carbon nitride, CXNY kind of systems. During this concentration of carbon and nitrogen, they have come up with different various structures, like, for example, C2N, CN, C4, and C3N4, with distinct properties in the electronic structure, which is very efficient for photocatalysis, thermoelectric, these sort of applications. And if the literature, it is huge. There are a huge number of materials present. So followed by a successful bulk scale synthesis of two-dimensional C3N, which is the monolayer polyaniline. It was a long-standing problem, and it was synthesized by two different groups, by two different techniques, in some polymerization technique and simple wet chemical reaction. So this is our parent structure. We have took this structure for our work, and then this has some intriguing features. For example, it is the only integrated bandgap semiconductor in this family of CXNY. It has ultra high state mass, higher than graphene, and low temperature ferromagnetism, much higher thermoelectricity, and optical tunability of the entire visible range, and many more. So what we did, we took the C3N unit cell. This is the unit cell of C3N. Actually, it is the 2x2 supercell of graphene with nitrogen doping. This is a synthesized monomer of C3N. And what we did is through self-adsorption, through this group 3 and group 4 and group 5 elements on the periodic table, after geometrical optimization on the through self-adsorption, we have gone through a different morphology, which is a monolayer dumbbell C3NX. We call them dumbbell C3NX because it looks like a dumbbell with a tilted side view. And the interesting thing is only these elements out of the periodic table have been able to form this kind of morphology. So we have found two different class of systems. One is integrated band gap semiconductors using the group 3, you can see group 3 and group 5 elements, and through group 4 elements, we have done the Dirac materials. So the motivation was we wanted to have the supremacy of graphene, but we wanted to have equally the applicability of CXNO. So we have found this and these two classes in a single family of materials, and this is the concern of our talk. Now this is the structure, full structure, just 2D sheet you can see, and this is the side view of the unit itself, and this is the add atoms on top you can see here and here. And this, as far as symmetries are concerned, the parent structure had mirror symmetry and centrosymmetry about that point. And after the dumbbell formation, you can see that only inversion symmetry is present. Only about this point you can see. Sorry. And the DFT calculations reveal the non-magnetic ground state, which is a time reversal symmetry, is also present. So this present the coexistence of inversion symmetry and time reversal symmetry give rise to Dirac cones around the Fermi levels. You can see the Dirac cones present in exactly at the Fermi level. And the interesting thing is only the add atoms contribute near the Fermi level. That is the carbon, silicon, and germanium. No other atoms contribute near the Fermi level, where the essence of physics lies. So we have the right in Hamiltonian, and if you can see that these atoms, only as I said that only these two atoms contribute near the Fermi level. So these two atoms, you can see the similar chemical surroundings. So you can put the mu0. And he found out that this is a linear dispersion, Dirac cone emerges. This is the linear dispersion mission, where it's in the previous plot. So this is the main section of our work. This is the so we have inversion symmetry, we have time reversal symmetry, and now due to high Z elements in our structure, we have strong SOC also. So we write down the Hamiltonian. This is the tight binding term. This is the famous Kane-Milley term, which was proposed by Charlie Kane and Jim Milley in 2004. And this is the applied electric field to break the inversion symmetry, so have some non-topological character. So this is we have applied the electric field in the Z direction, which breaks the inversion symmetry among the A and B sublattices. And the presence of SOC, you can see the absence of electric field. We have a non-trivial gap, which is the intrinsic SOC gap. And as the electric field increases, the gap closes at a certain critical value, which is this is the gap found from the dispersion relation actually. And beyond the critical gap, the gap again increases. So there is a topological phase transition, electric field induced topological phase transition from quantum spin-Hall state to a normal insulating state. And these are the parameters. This is for dumbbell C3 and SI actually. For G, it is 24 milli-electron volt, and dumbbell C4 is a light element, so SOC is not so strong. But the buckling length is huge, rather than the existing X-ins. So the SOC is very strong, and the electric field is very useful to break the inversion symmetry. It is the imaginary second nearest neighbor hopping in the Hamiltonian. The IT2, it was proposed by Halden actually in 2004. To break the inversion symmetry, but we have the spin term, so it restores the inversion symmetry, time reversal symmetry. Yeah. So to confirm this topological phase transition, we have plotted the Betti curvature for dumbbell C3 and G across the critical electric field. Below the critical electric field, we can see the quantum spin-Hall state, which shows the quantum. This is the band inversion you can see. And this is the exact topological phase transition we're talking about. This is a signature of topological materials because it shows band inversion. But beyond the critical electric field, what's the normal insulating state? There is no band inversion present. So this is one confirmation. And another confirmation getting more ambitious. We have plotted the one-year charge center along the KY axis. So you can see there is an odd number of intersections if you draw a line along the KY parallel to the KY axis. So below the critical field, you can see for this electric field, which is below the critical field, you have odd number of intersections, and you have this even no intersection, that is even number of intersections, which is a trivial phase. So this is the famous topological Z2 invariant. So if Z2 is 1, this is a topological phase, and this is non-zero, it is a non-topological, trivial phase. And this is the famous bulkage correspondence. We have taken 20 armchair nanoribbon in the non-periodic directions and plotted the band structure. You can see the topologically robust 8 states crossing each other, and the time reversal symmetry ensures the intersection at k equal to 0. You can see the up and down spins are connected at this point. And these states and these are immune to any kind of strong disorder or impurity, which leads to zero backscattering. So it's useful for spintronic devices. And now, as far as the 2D, we show that the 2D elements are topologically non-trivial, but what about the 1D systems? So we have also invoked the famous paradigmatic model of topology, which is the Schuster-Heger model in the 1D system. As we know that in our main structure, there is equal inter-unit cell hopping strength and outer unit cell hopping strength. So we have written down the Hamiltonian, and we have posed some shear strain for different twists of the dumbbells. You can see the twists here. For different twists of the dumbbells, for one, the atoms get closer, and for one, the atoms move outside from this. For the pristine case, the band structure, the gap closes. But when we apply shear strain along this plane, they're both gap phases. But you can see for one phase, there is a topological band inversion present, which is a V greater than W. But another gap phase is trivial, which is V less than, there is no band inversion. So this is a strain-induced topological phase transition due to the different twists of the dumbbells, which is and this is a specific case for this strength of the hopping parameters. And now this is another thing. You can now anyone can say that, but what about no strain? If you don't apply any strain, can you see the topological phase transition? The answer is yes, because we have if we do the half the concentration of the structure, because we have removed 2 atoms from the cell and we have half the concentration. This is basically where the stronger intra-unit cell hopping strength, and this is the stronger inter-unit cell hopping strength. And both are gapless. We can see the flat bands here, which can be confirmed from the dispersion relation earlier. You can see the existence of zero energy edge states for one case. Another one, there is no zero energy edge states. This is the extreme dimerized limits. We have checked through tight binding calculations and DFT calculations. They both agree that there is for W equal to 0. So this case actually, there is a high inter-unit cell hopping strength. There is topological phase transition. There is zero energy edge states, which says the topological non-triviality of the structures. And we have also checked the substrate effects because it was the freestanding case calculation. We have also stacked our structure between 2 hexagonal boron nitride monolayer, which is an insulator. And we have shown that the Dirac cone preserved, so it retains a non-trivial topology. So the substrate effects are good. And these are some calculations, some papers, which this is a 2021 paper, which shows that dumbbell silicon is synthesized experimentally. So our calculations, our structure is very much in the range of interest. And these are some existing dumbbell configuration of silicon atom defects on silicon nanoribbons, thermoelectric performance. So dumbbell geometry is very emerging now these days in 2D material systems. You can see many papers also. And it was claimed in 2015 that dumbbell structure can't be observed if the atom or monoatomic single layer have carbon atoms. But this is not true. Not true that our work proposed that this can be formed, and we have shown that. As the recent experimental reports on these kind of exine systems, topological effects, the edge states have been seen. And this is our publication, very recent publication actually, a few weeks back. And this is another work we are doing that is very interesting to think the topological thermoelectrics. What happens when the structure goes to a topological non-trivial phase? What happens with thermoelectric response? And acknowledgement, I want to thank my supervisor, Orko Bandhopadhyay, Autonomy for consistent support, and CSIR India for providing research fellowship, and thank you. And if you have any questions, you can ask. So, SSH?
Yes.
Oh.
So is the hermeticity guaranteed?
So actually, this is the second nearest neighbor hopping term. This is the nearest neighbor hopping type binding term. This is the next nearest neighbor hopping type binding term. And the spin is also included here. This is the Haldane model actually. To break the time reversal symmetry, they introduced the second nearest neighbor hopping term. So, and hopping along this line and hopping along this line is not equivalent.
So that's why I'm asking. And multiplied by
spin.
I.
Yes.
Is the hermeticity guaranteed?
Yes, sir. The spin is multiplied with the sublattice index. The sign is taken care of. Sign is taken care of. The sigma is plus minus 1 and z is plus minus 1. It depends.
That is a symmetric matrix.
Antisymmetric, yes.
Then
yes, antisymmetric. It depends on which sublattice you are in. Either.
I is mainly yes.
Yes.
I
Yes.
Square is minus.
Energy, right?
Energy.
What does it mean? It's not real, right? It's operator.
Yeah, but actually it was this to break that ambiguous symmetry. I don't know the diagram actually in this thing, but IT2 it was imagine I don't have any diagrams actually. Suppose this is a hexagonal structure. Hexagonal structure. This is a two sublattices. You can go from here to here, and you can go from here to here. So if it is a second complex second year hopping, so hopping along this is different from hopping along this. So that's why the complex conjugate is taken. So both sublattices are in the Hamiltonian actually. You can see the Hamiltonian here. This is the Hamiltonian I, and this is the sigma, the plus minus one, depending on which spin are talking about. For spin up, for spin down, for spin up it is plus one, and for minus one, and depending on which sublattice you are in, this is plus one or minus one. So this extra minus sign, if you complex conjugate, it will be taken into account. Yeah. Buckling means this out of plane layer, because the parent C3N structure had no buckling. You can see the parent monolayer, it has no buckling, it's planar structure. But when we put the adsorption, there is a buckling out of the plane contribution. This is a buckling. So if you apply electric field, you can break the inversion symmetry. You can assign different potential terms to the different subjects.
Have any more questions? Thank you,
Thank
Mr.
you.
Mungo.
Thank you.
Now, let us move to our next speaker, Dr. Shuman Dotto, a postdoctoral fellow from NCBS TIFR Bangalore.
Am I audible? Okay. Thanks, organizers, and also kudos to the entire team, and also for this opportunity that you have given here to present my work here. And yeah, my title was quite bold, right, and also quite scary. So this is why I put here a small movie. What you see here, these are highly jammed and packed spheres, which are somewhat in between of liquid and solid. So some of the features they actually have are quite similar to the solids because they are quite rigid enough, and also, but overall, some of the structures that for this kind of system that you see are quite similar to the liquids. So these are called glassy systems. Okay, and there has been debates after debates on this topic, and this has been treated as one of the most challenging and open problems in physics. And yeah, so there are more number of theoreticians that are working than more number of theories that exist in this domain. So we also try to understand this heterogeneous and glassy dynamics that people have been investigating for decades, and this is an all postdoc collaboration between us. And primarily today I will focus on this work with Vinay. But initially, I think here a lot of undergraduate students are there, and so this is why it's better to start with simple things and which is there for more than centuries. We all know Brownian motion, what it is. So Mr. Brown was doing experiments with the pollen grains, and what he that time saw was that this constant jiggling and wiggling of the particles. So this is to just give a simple example of that kind of motion. Yes, this example is not good enough, because this is under some confinement, but that's not right. So the simple example would be you put a drop of ink inside a pond. So then what actually happens, this particle moves through, and the ink particle that actually behaves like this way. So they just keep, you see this, these are the water molecules or water particles, and this bigger one are the ink one. So constantly these big particles face the constant bombardments of the other particles, and the overall outcome becomes something like this. So this was initially seen in 1827, and there was years after year, and people was almost couldn't understand much why this particle behaves like this. So this was until and unless Einstein's work that actually gives some idea, and this was later on Pera and then the Kepler. So what they showed that this kind of motion, and this is very similar to like a random walk, and this can be understood using the Fick's law of diffusion. Funnily, this was already there. So what it should say is that this kind of equation, I think we are all familiar with, and the underlying solution is a Gaussian. So what happens, so what it says that the underlying probability distribution of to find a particle in time t is a Gaussian, and that actually with time it flattens. Okay, so we have to keep in mind this physical picture of the diffusion, and we try to understand that how difficult and complex situation can be in the context of other complex liquids, like the classes. So liquids we have understood mostly, although liquid are hard to understand. So our focus would be this supercooled liquid, so which are very close to the glass, but this actually happens to liquids. This is at high temperature. You are actually cooling the system, and you see the jigglings are chronologically decreasing. And so we try to understand the dynamics of supercooled liquid, and eventually there was some experiments in 1990s. Started a lot of experiments try to because that time people tried to develop this confocal microscopy, and after that there were two experiments that happened in the same year, and both the papers got published in Science in the same year in the same issue. And what they show that for glassy system, the displacement distribution that earlier that was a Gaussian in case of a normal or a Brownian liquid remains no longer a Gaussian. And that there was a series of papers right after that also validated the same idea that for all different kind of complex systems, the dynamics eventually becomes non-Gaussian and remains non-Gaussian for some time. So things are not very simple here. So later on, Pinaki, who did BSc from here, he was there at University of Montpellier working with Ludovic Berthier and Walter Cobb, and that work gave the first understanding why this kind of systems show this non-Gaussian behavior. So this comes from some continuous time random walk model, and they give the first understanding of this heterogeneity, that why this displacement distribution become non-Gaussian. Later on, a lot of examples, more explorations from different angles, including even our work. We also joined the party in 2016, so we generalize it into the driven systems and many examples. But why are we telling all these things? There are more to do, more to understand. So the take-home message from so far story is that the underlying the displacement distribution for these complex liquids are non-Gaussian, and they remain intermittent for some time. So which is somewhat shown here. So this alpha 2 is something called the non-Gaussianity of this alpha 2 has been there has been there in the literature for some time, because this is also known as many different names with different names like the winter cumulant, the non-Gaussian parameter, different names were there, but for simple Gaussian, what happens that the fourth cumulant becomes the 3 times of the square of the second moments. So from there, one can easily construct this kind of non-Gaussian parameter. In glassy systems, what happens at high temperature, the behavior is quite similar to the liquids. The intermittency and the time scale associated with the heterogeneity is less. So means they remain non-Gaussian for small time, and the scale of the non-Gaussian remains very small. And at low temperature, when they are approaching the glass transition, the scale of the intermittency and the time scale associated with that grows with the decreasing temperature. So that is eventually the picture. But the way this non-Gaussianity was defined, there are some questions, because this is only limited up to 4th order. So, but you never know that what order of fluctuation can be important when systems are close to some kind of a close to phase transition or any out of equilibrium or maybe some catastrophic change. So we need to have a better measure for non-Gaussianity that gives us a better measure of understanding of the heterogeneity, or to identify the heterogeneity. So that we try to understand. So for example, so what can be the prescription? The earlier measures, this alpha 2 that I talked about, was limited up to 4th order. So it can capture the moments till 4th order. So now one can think of that we can also extend up to the 6th moment or 8th moment or 10th moment, but where to end? We don't know. So to address this thing, what we have done, we have taken the contribution of infinite order moments. So there are some of the ideas were already there. It has got a very strong connection with Kolkata as well. The way these kind of quantities are generally called as a negentropy. So this we have taken the form of this measure was earlier done by these Ivan Sanjay Kumar, who was an SM Bose, and Rajia Simon, who's from IMSC. They actually defined this kind of a quantity. So this is based on the relative entropy or the Kullback-Leibler divergence between this. Kullback-Leibler, why Kullback-Leibler? There was no answer. Just they were more popular. But earlier, people like Bhattacharya, they also defined some kind of a very interesting quantity. We are working on this right now. The work is not yet complete, but it also gives us similar kind of results as well. Bhattacharya means Anil Kumar Bhattacharya. Also, Mohanlanovic, who yes, he was there for a long time here. And also, Mohanlanovic distance also qualifies as a very interesting quantity at this thing. We are working on this. Probably in some future we can discuss about this. So how we are defining this thing is very simple. Let me give you the prescription. So for example, this was the picture of the supercooled liquid dynamics. So this is at high temperature when only two? Okay. Okay. So this was so for example, the definition is very simple. At a given time, the displacement distribution that you have at hand, you have to find out the nearest Gaussian associated with that, and then you have to find out the distance between them. So that gives how we define this quantity, and we repeat the exercises for different temperatures. So this was the earlier picture of alpha 2 that already was there in the literature. And now, for example, for same temperature, if we now evaluate this quantity, what we get are very surprising. So the peaks occur at different times, and for all the temperatures, the peaks are shifted to the higher temperature. Means what we earlier the scale and the time scale associated with heterogeneity that we thought that those are the scale of the heterogeneity was not complete. So we are indeed missing something. Now, if we correlate this, the time scale associated with this and this one, that actually diverges. As the system approaches the glass transition, the time scales diverges with each other, and the behavior between them forms some kind of loop. It means that at low temperature, when we are close to the glass transition, the deviation also increases between these two things. Do we understand this from some theory as well? This one? For this one, I think people have already tried. This alpha 2, They have tried.
It
Huh?
doesn't. It cannot be collapsed.
It cannot be collapsed because there are some indications. I'll tell you. Okay, so do we understand this picture, and can we actually frame this kind of picture from some theory as well? So we also try to understand this. So the simple, we already did some work. The funny thing is that we made the predictions earlier, then we do the simulations at a later time. So what we did, so we tried to model this kind of heterogeneous system using some continuous time random walk. So we think of the heterogeneous system as a summation of different domains, and that has got different scales of heterogeneity. And the scale of the domains is given by this row. So there exists a distribution of the domains, and in each of the domains you have the different waiting time distribution that categorizes the heterogeneity of the domains, means whether the domains are slow or fast. And now by using these prescriptions, one can actually have the displacement distribution of the Fourier Laplace space with this form, and then one can actually invert this thing by going into the real space to obtain the propagator, and from there one can actually evaluate this alpha 2 and delta SNG. So we did that and we got this plot, and in 2024 we actually saw that this actually indeed happens. So means the picture, the deviation between these two quantities, what we earlier predicted, actually follows the path. Not only that, what you ask that thing whether it is possible to collapse and make a combined story over that. Indeed we can. So, and the surprising thing is that scaling is not only common to the supercooled liquid, and if we have some kind of a we are smart, only one. This is almost if we are smart enough to rescale things properly, this line actually gives a common understanding of the passive liquids and also the active and also the shear systems as well. So this is a negentropy with some kind of 1 upon effective temperature. We are not understanding yet why this, can we actually have a theory of that? So this is still open, and yes, this contradicts to some of the earlier understanding that came this year. With this, I want to just summarize. We recently published this work, and yes, so the one-liner of this work is that the entropy measures are more robust, and that actually with respect to the existing measures that we had for heterogeneity, and we are trying to validate its robustness in both equilibrium and output equilibrium context. ICTS recently issued a very nice commentary on this work. You can have a look into it. And these are some other things that I also work on with Chandan Pinaki. They were also from this place. Thank you for your attention.
Since we are running out of time, so if any of you has any question, you can always contact with the speaker after the session. Is it okay, sir?
Yeah, quite sure.
Thank you. Okay. Now, the last speaker of today's afternoon session is Dr. Momita Sarkar. I'm so sorry, Dr. Momita Noshkar, a postdoctoral fellow from IMSC, Chennai.
So, good afternoon all. Today I will talk about creep response of soft glassy systems when subjected to a constant shear stress. So first, this is the outline of my talk. First, I will introduce two amorphous materials. Then I will I will show you some analytical prediction of the creep flow rate in soft amorphous systems. And finally, I will present some recent numerical observations on creep in a thermal or glassy system, followed by a summary. So people are always curious about amorphous materials because they exhibit partially similar behavior to both solids and liquids, in the sense that their microscopic structures are liquid-like, that is fully disordered, whereas their macroscopic or bulk behavior is solid-like, that is they can sustain a certain amount of applied stress. And due to the absence of long-range order in those amorphous materials, it is very difficult to deal such systems theoretically. Nowadays, numerical simulation has been emerged as a very useful tool. Uh, and the world of such materials covers an extended range of length scale, starting from some thermal systems like metallic glasses, polymer glasses, to a thermal system like granular solids. And due to different interparticle interactions, we need different numerical models to describe the behavior of such distinct systems. And I have here I want to mention that I have worked on these soft glasses systems, specifically these colloidal glasses. So what controls the dynamics of such materials? So for thermal systems like granular solids, density and load are the main control parameters. But for the thermal systems like these glasses systems, where constituent particles are small enough to be affected by thermal fluctuation, their temperature also rules the dynamics along with density and load. Now combining these effects, first time in 1998, Liu and Nagel proposed a speculative phase diagram of jamming, where the center of this phase diagram represents the jammed system, which can be unjammed either by increasing temperature or by increasing load. And if we are concerned about the glassy or thermal systems, then this phase diagram also indicates that the glass transition temperature can be lowered by imposing some stress, and also the yield stress of the material can be lowered by inducing some thermal fluctuation. Now, this yield stress is another characteristic property or defining property of those amorphous materials. And this yield stress actually is the maximum amount of stress that the system can sustain without any plastic deformation. So if the applied stress is below the sigma y yield stress, then it shows reversible elastic deformation. And if the applied stress is beyond sigma y, then either it shows irreversible macroscopic fracture if it's a brittle amorphous, and if it's a soft amorphous, then it shows a steady flow. Now, if this in the steady flow properties are analyzed, then most of these amorphous systems are found to follow this power law behavior, which is known as the Herschel-Buckler law. And in the low limit of this power law fit, we can determine the yield stress from of these materials. So how are these glasses prepared? Glasses are prepared by rapid cooling from melt, so that it enters into a metastable state, supercooled liquid, and departs from the usual crystallization process, and it enters into the metastable state. And then over time, the constituent particles rearrange themselves, and after a certain temperature, the system gets frozen, kinetically frozen with some disordered structure, and then we call it a glass. So this is purely a non-equilibrium phenomena, and the glass transition temperature of these glasses are not uniquely defined for a particular material. It's strongly dependent upon the thermal and mechanical history of the materials. And all of you know that in today's life, glasses are enormously used for their many useful properties. So it's important to study both the dynamical and mechanical behaviors of these materials. So now, when do we observe such creep response in the soft glasses? So if we apply a constant stress, a certain constant stress to a glassy, soft glassy system, then in general we observe three different regimes in the strain evolution curve. Initially, there is an immediate transient elastic behavior, which includes this oscillatory part, and beyond that, the system flows plastically. Now, this plastic flow depends upon the type of material, whether it's thermal or athermal, and also the amount of strength of the stress. So, if the stress is very high, then it flows immediately. But if the but with lowering the stress value, this strain then increases very slowly, and in most of the glassy systems they follow some power law behavior. So this very slow deformation is known as the creeping behavior. And instead of thermal system, if we consider an ethermal system, then it's generally observed that the strain gets arrested with some fixed constant strain value. Now, very recently in that paper, authors have analytically predicted the strain rate behavior in this creeping regime for both the ethermal and thermal system. And for glassy, this thermal system, they have predicted that the strain rate decays with inverse of time, and this is material independent, whereas for ethermal system it's material dependent, because this nu is dependent upon beta, which is a material specific parameter. Now, before presenting the results for glassy system, first I want to show you this recent results from this paper. So here first author Shumanda is present here. So they have, and also I want to mention the model because I have also worked on the same model. So authors have simulated a microscopic 2D binary Lennard-Jones system by molecular dynamic simulation, and the temperature has been maintained by distributive particle dynamics thermostat, and the constant stress has been imposed by a feedback control mechanism. So with that, and using a well-annealed GQ state, they have studied the macroscopic behavior in terms of strain and strain rate evolution. So as I have already mentioned that for ethermal system, below the yield stress, the system is found to get arrested with some constant strain value, and above yield stress, it flows. Now the corresponding strain rate shows non-monotonic behavior, where below the stress it decays following some power law, and above the stress it ultimately reaches this steady state flow. So now I have used this same model, but this same GQ state now I have been thermalized to 3 different temperatures, always below the glass transition temperature of the system. And we observed that compared to a lower temperature, at high temperature regime, this creep or slow deformation is much more prominent, and also the system flows gradually here compared to the lower temperature. And if we look into the strain rate evolution, then we found this interesting universal property that has been analytically predicted, that in each plot, if we look into each plot with lowering the stress, we can see that this strain rate approaches this analytical prediction. So although the thermal histories are different, that is the system is residing at different potential energy levels, but still we can see this universal property either in the limit of low temperature or in the limit of small stress. Now we have determined both the static and dynamical yield stress, and for that we have first denoted this fluidization time from this minima position, and plotted the inverse of tau f with applied stress. And from this fitting or this cut point, that is in the limit of large fluidization time, the static yield stress has been determined, and the dynamical yield stress has been determined from this steady state flow properties. Yes. Okay. And we found that both the static and dynamical yield stresses decrease with increasing temperature. Maybe it's due to the thermal fluctuation comes into play now. Now, how does the system evolve microscopically? So for that, we have taken some snapshots of local non-affine deformation for several stress values at several time steps. And here we found that some plastic, heterogeneous plastic deformation that can be considered as an onset of flow that already starts from this clipping regime. And during the flow, the system forms such shear band kind of structure. And otherwise, if we decrease the stress, then this heterogeneous spatial plastic deformation still appears, but they grow very slowly with time. Now we have studied the distribution of this non-affine deformation at two different stress values. So this primary peak indicates the glassy behavior, and the spread in the tails that actually indicates the system is creeping. And at lower stress value, this spread still exists there. That ensures that the system, unlike the thermal system, the strain is not getting arrested here, but the system still creeps here very slowly. Now, from these snapshots, we are not assured that whether the number of active sites are constant, only their amplitudes are increasing, or the number of active sites itself increases. So for that, we have checked the dynamical activity, and so here we set a, for that we have set a cutoff of this bitumen, and based on that, we have basically do a binary mapping of these snapshots, and the number of active sites has been studied with time, and we found that that increases with time. So that means the number of active sites also increases, not only their amplitudes, and also it follows a similar trend as the macroscopic strain behavior. So from that we can say that the macroscopic behavior is strongly connected to the microscopic behavior. So, in summary, we can say that unlike the thermal system, here we didn't found any arrest, but the system creeps for a long time, and at high temperature, we found the prominent creep flow, and the system flows also gradually there, and that analytical prediction of the strain rate that decays with inverse of time, that we observed that our model follows that either in the limit of low temperature or in the limit of weak stress, and both the static and dynamical yield stresses they decrease with temperature. And from the microscopic response, we observed that plastic rearrangements that can be considered as onset of flow that starts already during the creeping regime, and the system flows through the formation of a shear band, and we found a strong connection between the macroscopic and microscopic behaviors, and but the main question still remains that and we are not assured whether the system in the limit of low temperature and stress, what will be the actual behavior in the long time, whether it creeps forever or even after infinite time it eventually flows. So that still remains a question here. So thanks to my guide, Professor Pinaki Chaudhary from IMSC, and also my colleague, Dr. Shuman Datta, and from NCBS, and Dr. Vinay Vaibhav from University of Milan for many discussions. And also thanks to IMSC supercomputing facility, and thanks to organizers for selecting me to deliver a talk here. And thank you all.
Like these theoretical predictions.
Yes.
So what kind of models are good with raw sulfide and calculation is always impossible?
No, analytical, actually their approach is very much Landau theory-like. So they define a property here, this transient yield stress. And their main assumption was that this plastic flow is governed by this difference between the applied stress and this transient yield stress. And this is considered to be a smooth function of this gamma, and then by doing some Taylor series expansion, ultimately they predicted this. So there is some derivation actually.
On page 12.
Yes.
Yeah, this object, this square, what is it exactly? What is it saying?
It is actually the yes. Actually, instead of mean square displacement, here we have taken this non-affine deformation. So we are actually shearing here, shearing the system here. So if we take the normal mean square displacement, then the actual displacement will be masked by this our shearing effect. So to remove this, actually in this paper they have followed this technique more systematic. So actually instead of taking the difference between the particle positions, they have actually considered the interparticle difference between the interparticle separations. Yes. Share bandings. Light blue means actually here. So with some plastic deformation is there, but amplitude is lower actually. This displacement, this quantity, minimization of this quantity. D to mean, D to mean. No. Displacement. This is a snapshot of displacement.
So this is not hardly kind of algorithm you are using here.
MD actually this is the main Hamiltonian. So Varley is used here. I think this first term due to this first term Fij. This is from this gradient of potential.
So you are using that.
This is actually done by lamps. So okay.
We do not have any more questions. Thank you.
Thank you so much.
Okay, this concludes the fourth and final oral presentation session of our two-day national conference. I now hand over the mic to Shavik.
Thank you, Turni. We will now have a tea break, and in the meantime, we are compiling all the poster and oral presentations. So have a tea and meet you after 15 minutes. So after that, the certificates will be distributed.